All right. Okay, so before we finish, we'll talk about lattice gauge theory. So then the strategy for non-abelian gauge theory to study is low energy phenomena is to put the gauge theory on the lattice, and then you can it's discretized as an infinite. In a field theory, the most difficult part is that you have infinite number of degree freedom. But then suppose you put on the lattice, you're approximating infinite number of degree freedom by finite number of degree freedom because you're already on the lattice. You will see later on explicitly what we are doing. And then you can actually perform the computation, mostly numerically on the computer. But you can perform the computation non-perturbatively in the strongly coupled regime of non-abelian gauge theory. That's the strategy. That's the story about lattice gauge theory. So here you see that our in our strategy of to quantum gravity, especially what we call loop quantum gravity, it is a non-perturbative quantization of gravity. So we have to do quantum gravity non-perturbatively, and also background independently, because as I emphasized last time, that generativity now is SU2 gauge theory, non-abelian gauge theory, but also it is background independent. It doesn't depend on the metric. And also we don't really want to do the perturbative calculation because you see our formalism coming from Hamiltonian analysis. We want to do start with this Hamiltonian formalism and do something like we do in quantum mechanics and replace those variables by operators and so on. This is really a non-perturbative quantization. Yeah. So then a natural starting point is to make the quantization similar to lattice gauge theory, because we had some experience on non-perturbative quantization in lattice gauge theory. Okay, so now what we are going to do here in loop quantum gravity. So maybe I should give you firstly a definition of loop quantum gravity. Loop quantum gravity before we actually go into the detail. Quantum gravity. Okay, so this is so firstly it is an attempt of because it's an attempt because at the moment there's no complete theory of quantum gravity yet, so this is just one approach of non-perturbative background independent formulation of quantum gravity. Quantum gravity so there are formulations in 4 dimensions. Most of the time, the most powerful formulation is in 4 dimensions, but there is generalization to arbitrary dimensions as well. So in 4 and higher dimension.
Excuse me, sir.
Okay. There is a question?
Yeah. So can you tell what do we exactly mean by background independent here?
Okay. Yeah, because you wasn't in my generativity class. So here is because generativity is background independent. So being background is a space-time background, means metric. So background equals to space-time. So space-time equals to GAB, metric. So here for general relativity, the gravitational field is described by GAB.
Yeah.
Okay, and therefore GAB is your dynamical variable. GAB is the dynamical variable in Einstein equation, and then GAB is space-time and is background. So which means the space-time and background itself is the dynamical variable in general relativity, in gravitational field. Okay, so therefore, gravitational field for Einstein equation doesn't depend on any pre-assumed background space-time, because background is the dynamical variable. So this is very different from all different kind of other field theory, because for example in Maxwell theory you have to assume that you have a metric, which is usually a flat space-time, and then you have but then well, including all other fields, Dirac theory and scalar field theory, it's the same. You have to assume a metric, but for gravitational field, this is very special. We don't really, Einstein equation doesn't really assume a metric, because metric itself is a dynamical variable. Okay, that's
okay. Thank you.
And that's all the resource of there. As I mentioned before, there are so many differences between gravitational field and the ordinary other field theories. The resource is exactly this background independence. Yeah, so this is very important in gravity, and the point of the loop quantum gravity is keep this feature seriously in quantum theory. Okay. Yeah, very good. So,
okay. Thank you.
Is there other question?
No, that's it.
Okay. And yeah, so this is the feature of background independence, and also the non-perturbative. It's also coming from Einstein equation. We know Einstein equation is non-perturbative, and you can get all kinds of non-perturbative solutions. Of course, you can get perturbative solutions and get gravitational waves and so on, but you can also get a lot of important non-perturbative solutions, especially for black hole. And also, the purpose of quantum gravity is for those non-perturbative phenomena. Because for black holes, there's black hole singularity, right? And the purpose of quantum gravity is to solve this the problem of singularity. Yeah, and those singularity always exist in non-perturbative regime. For example, for black holes, and it's clearly it's non-perturbative. It's a non-perturbative object in gravity. And also the beginning of cosmology, the beginning of the universe, you have Big Bang singularity, and that's another non-perturbative regime of gravity. And these singularities always exist in strong gravitational field. And strong gravitational field, it means that it's strongly coupled regime. It's strongly coupled regime for gravity. You can't over there. You can't really do perturbative expansions in terms of G Newton, right? Because over there gravity is very strong. So that's the reason why we have to study non-perturbative quantum gravity and also background independent quantum gravity. Yeah. And so because of this feature of non-perturbative and background independence in our quantization, we better use the strategy of lattice gauge theory to perform the quantization. Okay, because that's probably the right tool to work. Okay, so I hope I make this clear for everybody. So how to actually do this? So now let's come to our spatial slice. This is our spatial slice sigma. So being so-called lattice gauge theory, so we have to first build a lattice. So here let's consider just a cubic lattice. So well, of course this is dimension is 3, but it's complicated for me to draw 3 dimensions. So I suppress 1 dimension, 3. So let's consider this is a cubic lattice. So for simplicity, let's consider just it is a finite cubic lattice. Finite means that you have finite number of vertices at this moment. Lattice, and I call this lattice gamma. And in the terminology of loop quantum gravity, people also call it a graph, or a graph. So, but this graph is just now a finite cubic lattice. Okay, and namely this gamma is it is z it is z3, but yeah, finite. Well, usually in lattice gauge theory, people write the lattice is z3. But since we talk about this finite wall, but this finiteness is not so important. So let's just say this is a cubic lattice. Ignore the property that it is finite or infinite. So suppose this is infinite, then this is just a Z3. Gamma is just a Z3. So it means, well, to be more precise, this is vertices of the gamma. Gamma is Z3. Is isomorphic to Z3. Z means all the integers. Yes. So yeah, Z3 means triple of integers. So well, then this is all the vertices are of this lattice. So then in the for this lattice gamma, so we define two sets. So we denote two sets. We have some notation for two kinds of sets. So firstly, the set of all edges or links for all the edges, I will call it more precisely all oriented edges. Edges, I will call it E gamma. Yeah, so it's all the edges. So all the edges. So here, edges, oriented edges means that for each edge you have orientation, because each edge is a curve, and all the curves are related to certain parameterization of the curve, and then you have orientation. So I will come to that, and this is useful because some reason that I will talk about. And you also have the set of all vertices. So I will call it V gamma. So this is just some notation I will frequently use in the following. So all the vertices is the set of all the vertices I will call it V gamma, and set of all the edges I will call it E gamma. So here you can locally look at a vertex. Let's call this vertex V, and then each vertex connect to 6 edges. So you can view this is like a coordinate system, but the lattice only has coordinate axis. Okay, so you have 3 edges. So I mean, let's fix the orientation such that to the all the orientation are to the positive direction of the coordinate system. Yeah. Which means this is the first x1 direction, this is x2 direction, this is x3 direction, and all the edges are oriented toward their positive direction. So which means these edges point this way as well. Okay, so now you have in total 6 edges at the vertex. So which means all vertices are 6 valent. So you have 6 edges at each vertex. And also, so here you have some neighboring vertex, right? You know, this is lattice, you have neighboring vertex. So this is V. So in our notation later on, I will call this is x2. So I will call this point v plus 2 hat. Yeah, and then there's another vertex here that I will call v plus 2 times 2 hat. Yeah. And here this point I will call v plus 1 hat, and this point we are called v minus 1 hat. You see what you can see what I mean. And also this edge, so I change the color. This edge I will call it E2 at V. Yeah. And this edge I will call it E1 at V. Right. And then this edge, yeah, then it's outgoing, it's outward pointing from V minus 1. So this edge I will call E1 at V minus 1 hat. So you see so here it is just some labeling system for the edge. So you can see that I can uniquely label those edges by using their direction and the vertex where it's starting from. Okay, so is there any other notation I need to? Oh no, that's it. So here you can see we have this label for all the vertices, and we have this label for all the edges. Okay, and this lattice is adapted to certain coordinate system. Yeah. Certain coordinate system. Okay. So now, well, to arbitrary, you just choose an arbitrary lattice. All right. So then, once we build this lattice, we are going to discretize all the dynamical variables. Before, we have this smooth field, namely the external connection and the density type stride. Okay, so they are all smooth fields. But then we have to, so we have so-called discretize those smooth fields to our lattice variables. And the point here is that, because for smooth fields they have infinite number of degree of freedom, but the point we want to, the procedure here is that we approximate those infinite number of degree of freedom by finitely many degree of freedom, and those finite number of degree of freedoms are those lattice variables. So firstly, Firstly, on each edge, we are going to define something called holonomy. Each holonomy is a SU2 group element. This is called holonomy. Or Wilson line. But this just means two different things. And for physicists, this is called Wilson line. For mathematicians, or people, geometrists, it's called holonomy. But we are just the same thing. And secondly, we define Pj of E. This is a vector in R3. This is called gauge covariant flux. So you see this holonomy, they are the lattice variable replacing connection or gauge potential, external connection. And this gauge covariant flux is the lattice variable in replacing the this E, the density type stride. So here I just tell you some names. So I will give you definition in a moment. Yeah, in this lecture. And here, so this is for all edges. For all edges. Okay. So here the lattice variable. Well, in case of the in case that you have finite lattice, the lattice variable is clearly finite. But in case you have infinite number of edges in infinite lattice, the lattice variable is still infinite. It's still infinite. But in most of the calculations, we actually assume that this lattice is finite. Okay, so here's the point of the lattice discretization. Is approximate a field theory by a system with a finite number of degree of freedom, and we should be able to recover the field theory by lattice refinement. Lattice refinement, or what we call continuum limit. So it means that we, although we discretize our space by using a lattice and define all the variables on the lattice, discretize the smooth field on the lattice, but we should be able to recover the smooth field if we infinitely refine the lattice. We keep refining the lattice in the limit, and so that the lattice, the spacing of the lattice become infinitesimally small. Then we should be recover our field theory on the continuum. Okay, so this is the logic. So so far everything is still classical, right? And that's why I say it is the preparation of the LQG quantization. And at the moment, we're just trying to define those lattice variables, classical lattice variables, and then we quantize those lattice variables afterwards. Okay, so now let me first consider holonomy. I'll give you a definition. And this is definition for holonomy. Okay. Now, given this H-Tuck connection, one form, it is an SU2 gauge potential. So one form. This is one form. Given that and a oriented edge. So what is an oriented edge? E. So I call this oriented edge E. So E, this edge is just a curve, right? Being a curve, it's a map from 0 to 1, this interval, to embedded to sigma, yeah. And namely, I consider the parameter running from 0 to 1 is S. So this S mapped to a given an S, you get a point E of S and belongs to the space sigma. Yeah, that's why you get an S. So then that's why, and we we call, well, this map, we consider this map to be simple, namely it is analytic. It is an analytic curve. Namely, this map is an analytic map. Yeah, it's even better than C infinity, even better than smooth. Okay, and this curve is, well, this is a curve in the manifold, and the beginning point is 0 and end point corresponds to 1 in the parameter, parameterized by S from 0 to 1. Okay, so this is an edge given a connection field and an edge. Given those two things, and the tangent vector. So again, the notation, we denote the tangent vector of the edge by following tangent vector of E is denoted by this is tangent vector of E is DDS in our notation, DDSA using abstract index, and these I will denote by E dot, just E dot A, yeah. And this E dot A, well, using a coordinate system X, this is just mu equals 1 to 3 dx mu ds partial mu. Okay. So using coordinate system, we can expand this tangent vector. This is something we have learned a long time ago. Now we can define the holonomy. This is defined to be so-called a path-ordered exponential. So I will explain what it is. So it is exponential and exponentiating a path, a integral over this curve. S, integrating of the parameters and AAI, and E dot A contract with the tangent vector tau half. Well, it is just the connection one form integrated along the curve. This is nothing but in the exponent. It is just connection one form integrated along the curve. But this is connection one form as a matrix. So here it is not AAI integrated on the curve, but AAI contract with Pauli matrices. So here tau I is a matrix minus I sigma I from 1, 2, 3. So sigma is a Pauli matrix. Okay, so that's why in the exponent, this is a matrix. So you are integrating a matrix along the curve. And that's the reason, and being matrices, they are not commutative. Yeah, they are not commutative. So that's the reason why you have path ordered exponential. Yeah. So it relates to path orientation. That you see the edge must be oriented. So firstly, because you have a parametrization of the curve, and there is orientation because you know where is 0, where is 1. So there's orientation. So this orientation is just the flow of the parameter. And secondly, you are integrating a non-abelian matrices, non-commutative matrices, and then that's why when you're taking exponential, you have to taking care of the path order. You are integrating this integral. You are exponentiating this integral and integrating non-commutative matrices. So I will come into more detail about this path order. Show you explicitly what it is. So I mean, then using coordinate, you probably see it more, see the formula more explicitly. So a mu I and dx mu ds. How so this quantity. Okay, and this p It is what we call path ordered exponential. So P exponential. Path ordered exponential. Path ordered exponential. This path ordered exponential, if you have learned some little bit about quantum field theory, you have seen this path ordered exponential already. Recall that in S matrix, in quantum field theory, recall that S matrix is a time ordered exponential. It is a time ordered exponential. Minus I integral from 0 to t, and your dt prime integrating your interacting, your Hamiltonian in the interacting picture, right? So this is, or even in quantum mechanics, if you go to the interacting picture of quantum mechanics and computing the transition amplitude in quantum mechanics, you will see, you will define the transition amplitude or S matrix to be a time ordered exponential of the Hamiltonian. Yeah. And yeah, this is because your Hamiltonian is time dependent. Okay. And you see, and they are really the same thing. Yeah, and very similar. It's very similar. So here you can view this A. It is just your Hamiltonian in the interacting picture, and time-dependent Hamiltonian. And so this time-ordered exponential, it is here the path-ordered exponential, because here the parameter S is the parameter of the curve. And here, although here the time will be the parameter. Okay. All right. So here we often have this notation. We say AA, it is the matrix. AI, tau I. It is a matrix. And it is also belongs to the SU2 Lie algebra. Because this tau I or Pauli matrix, they are just a generator of SU2 Lie algebra. Okay, and then we often write, and with this AA matrix, this is the matrix valued one form, or the Lie algebra valued one form. Yeah. So, and this is actually the general feature of the so-called connection field or gauge potential in gauge theory, is that the gauge potential or the connection, it is always a Lie algebra valued one form. So whenever you see something called connection, then it must be a Lie algebra valued one form. It's just depend on what is the Lie algebra. It's depend on the gauge group. Okay, so now with this matrix AA, we can just write this holonomy to be a path ordered exponential, and this integrating this one form along the edge. Okay, so this is just a short version of the above form. Okay, so this is the definition of holonomy, and now I've talked more about this path ordered exponential. So in case you are not familiar with, or in case you are not familiar with scattering amplitude and time ordered exponential, so let me give you some expression for this path ordered exponential. So now the holonomy equals, you can try to expand this exponential, and this path order, you can view this P as an operator, and this operator is a linear operator. Okay, so one sentence before we come to that. So another analog between S matrix and holonomy is that here this S matrix, or this scattering amplitude, is a time order exponential of the Hamiltonian, and the Hamiltonian is a self-joint or Hermitian operator, and then this S is a unitary operator. Time ordered exponential Hamiltonian, it is a unitary operator. This S is a unitary operator. So here it is very similar. So here this the analog of the Hamiltonian, here it is just a connection field. The connection is a Lie algebra value, SU2 Lie algebra value. Yeah, and then you exponentiate. Yeah, what you get is an SU2 group element. So it's like exponential map in the Lie algebra. So this H of E belongs to SU2 group. Belongs to SU2 group, but this AA belongs to small SU2, which is usually the notation for the Lie algebra. And then here, this is the Lie group. Yeah, so then the conclusion is that holonomy, because the connection field is Lie algebra value one form, and then the holonomy belongs to the Lie group, belongs to the gauge group. Here it is just SU2. Okay, so now let's come to this path order exponential, and now you can just consider this P as a linear operator, and then you can formally expand the exponential. What you get is from 0 to infinity, 1 over n factorial, integral 0, 1 ds a e dot a. Okay, so now I just use the matrix a. Okay. Well, I will further simplify my notation. I will call just AA e dot a. I will call it a. I will just call it a as a function of s. Yeah, so this is again a matrix. A is a matrix. I will just call this AA. All right. Now, well, I can view formally this P as a linear operator, namely commute with sum P 0, 1 S A S. Sorry, so here it is power n. Here is power n. Here is power n. So P act on the monomial of integral over A. Okay. Now you can expand the sum. Well, the leading order is n equals to 0, which is just 1, and P act on the identity. The identity is independent of the path order, so it's just 1, and plus the linear order 0, 1 ds ks. Well, linear order is involved. You can view this is P act on this, but well, it is just a simple integral, so there's no ordering. So this is just a single matrix integrated, and P act on a single single matrix. It's just the same matrix because P involved because P involves the non-commutativity of the matrices. Yeah. So yeah, you have only a single matrix. P act on it. It's nothing. There's no any non-commutativity involved in this term. Well, it involves non-commutativity